Hey everyone! In this video, we're going to really look into those graphs that we were looking at last time we were together and kind of go further. So we're looking at all those logarithmic graphs. So a couple things we saw already is we were talking about parent functions, right? So when I'm talking about parent functions, the big thing, just to think about our exponential versus our parent function again, we know for exponential, our parent function is going to be y equals b to the x. B can be a plethora of things, right? We know b cannot equal 0, b cannot equal 1. It's not going to get us a function that we want. So either b is greater than 1 or it's in between 0 and 1. So those are the things we're thinking about for exponential. So we know we have more options. And then now with logs, same idea. Log base b to the x. And b has those same requirements, right? Base still can't be 0. Base can't be 1 if I want it to be a function. So all of those are still going to be true. Now I'm just throwing it all the way back for a quick minute. We know for a quadratic, y equals x squared would be a parent function. We know for a cubic, y equals x to the third. For an absolute value, y equals the absolute value of x. And even for a square root. All of those are our parent functions. It's the most basic form of what that function is going to look like. So exponential and logs, they live this different life. Because they're hand in hand and they're inverses of each other, they live that life where they have more options of what that parent function would be. But b is the standard. So reminder for my parent function, coming on back, if parent function is y equals b to the x, right? That's my parent. We're looking at transformations where y equals a times b to the x minus h plus k. Now, as a reminder, sidebar over here for a quick second. If I think about y equals x squared, we know that can look like that vertex form, but we see all of our transformations right in there. That h and k represent this same idea, where h is my horizontal shift. We're going left or right with that. K is our vertical shift. And with A, that's where you're going to have that stretch or shrink. It's going to be whether it gets higher or lower there. So it's like that dilation piece to that happens in there. So getting into what we kind of recapped yesterday, that same thing, while my parent function is log base b of x, where b, we know the requirements at this point. If that's my parent function, any of our transformations can look like a times log base b, you have x minus h plus k. Now in there, all the same things are true. H is going to be my horizontal shift closer to the x. K is going to be my vertical shift. And that A in front, that's your stretch or shrink again. That's like that dilation piece that occurs. So that being said, having that formula, we kind of saw ideas that happened yesterday, but basically, before I even go into it, I had another slide in here that I wanted. Whatever. So all those pieces, the idea of what we're having here, when I go to graph this, Reminder, what I'm going to do first, I'm going to actually graph the parent function. I'm going to graph y equals log base 4x here. That's my parent. Things that we learned yesterday is that that's going to pass through the point 1, 0. And then that has this asymptote of x equals 0. So that's my parent function. Now, what I see here is that this had a horizontal shift to the right too. So same kind of idea in there. But if that shifted right too, as I have here, so this is my y equals my log base 4 x minus 2, what's happening in this case is I'm also going to move over my asymptote, right? My asymptote is going to be x equals 2. I move 2 units to the right as well. So opposite of our exponential, this is shifting right and left. Horizontal shifts get that asymptote to move. Remember, in the exponential, the vertical shift got that to happen. Okay, looking at this again now, I won't draw the parent function out. The parent function would be y equals log base 3x, but I won't draw that part out. The idea that I know here now is that -3, that's my vertical shift in there. So that original point of 1, 0, that's going to come down 3. So eventually I will hit that x-axis. There's nothing stopping me there, but there's no shift along there. So with this, my asymptote is still x equals 0. So we've got a vertical line as our asymptote around here. Now I've got 2 shifts here. I'm shifting left 4 units and down 2 compared to the parent function. So again, when I think about that 1, 0 being that point that I know, so I'm going left 1, 2, 3, 4. And I'm going up 2. Oh, I wrote down 2. Up 2, sorry about that. Positive. So with that being said, I'm drawing my log. And what happens here is x equals 0 was that shift. Remember, the horizontal shift is what takes it. So we're going 1, 2, 3, 4. My asymptote's at x equals -4, that means. Okay, and one more time. Getting one more sketch in there. Same idea as we've been doing. This shift. Remember that parent function would have been at 1, 0. Now I'm going 2 to the left, down 1. And my asymptote's going to be 2 to the left. And to recap one other idea, if we talk about our end behavior as x approaches, let's do positive infinity first. And y is approaching positive infinity slowly, but it's getting up there. And then remember, it's going to change to x approaches -2 here, because that asymptote's like that blocker, that x equals -2. That's when y is approaching -infinity. All right, guys, you're going to have a practice to work on when we come back, just to kind of get the rhythm of all these log graphs and their transformations. Thanks so much for watching.